Here we are with video number 3, and we start by maybe defining what a Riemann sum is. And so we call these Riemann rectangles because they use this pattern of adding very specific terms. And so when we talk about a Riemann sum, we're talking about adding, and for you pre-cal people, you might remember this symbol, the sigma symbol, which tells me we're adding things. But we're adding things of a certain pattern. And what Riemann came up with was this idea that we're adding terms that follow this pattern. We're multiplying a function value, times a change in x value, which corresponds directly with drawing rectangles, because we said the function value is the height of the rectangle, and the delta x would be the base of the rectangle. And the sigma means we're adding a bunch of areas of these rectangles. Remember, when you multiply a function height times the delta x base, you're going to get the area of a rectangle, add up a bunch of rectangles, and there you have a Riemann sum. So when you hear the word Riemann sum, this is kind of the notation that you should envision. We're multiplying a function somehow with a delta x somehow, and we're adding all those products. That's what a Riemann sum is. And so Riemann rectangles follow that pattern as well. And so what we're going to do is we're going to draw and calculate some Riemann sums, which can be equated to Riemann rectangles. So in this first example, we're going to use a left Riemann sum. What does that mean? We're going to start from the left side, and we're going to draw rectangles. Now, it says specifically with one subinterval to approximate the area between the curve VQ of t and the t-axis between time 0 and time 2. So we're still looking at the same shaded region, right? We're still looking at this that we're trying to approximate. I can't figure it out exactly because I have that curve, and so I'm going to use a left Riemann sum with one subinterval. One. If we're doing one subinterval, that means that's the width or the base of the rectangle. And so this would be my delta x. My delta x is this. Now, there's a formula that we can use that says if you know where you're starting and you know where you're ending, if I'm starting at A and I'm ending at B, then subtract B minus A and divide it by the number of rectangles or subintervals you need, and that's going to give you the base of the rectangle. And in this case, we don't really need that formula because we know we're only looking for one subinterval. We are starting at 0, we're ending at 2, and so that base of that rectangle is going to be 2. But if I had used the formula would have said 2 minus 0 divided by one subinterval, and that gives me 2. So my delta x is 2. My height, because I'm using the left side, I'm going to start from the left endpoint, and I'm going to go straight up until I hit the curve. This function value at 0 is going to represent the height, and so I'm going to approximate that shaded region with this one rectangle. Is it a good approximation? Well, I guess we know that the answer has to be bigger than the area of that rectangle, because I can see that there's a shaded region that didn't get bounded by that rectangle. But it'll give us a way to start, right? And so we're going to say that the left Riemann sum is equal to the function value, which is v, and now we're using the height at t0, right, when my input is 0. So I'm going to say the height is going to be what v of 0 is times my delta x. Now, we already calculated that the delta x is 2, and we can look at the picture and we know that v of 0 is 1, and so my answer here is 2. So this is my approximation for example 1. The fact that this rectangle has an area of 2, is that the area of the shaded region that we want? Well, no, but it's an approximation. It's an underestimate, and the more rectangles we make, the better the approximation will be. So let's look at another example, example 2. Now we're going to do 2 equal subintervals. Okay, so now delta x, the width or the base of the rectangle, is going to be 2 minus 0 divided by 2. Well, that's 1. That's telling me that the width or the base of the rectangle here is 1 and 1. So I'm going to have 2 rectangles. And because I have 2 rectangles, the height and their left, I'm starting from the left endpoint, this is going to be the first, and I'm going to go all the way until I hit the end of the first subinterval. And then at 1, I'm going to use that height, and I'm going to go all the way across, and that's going to be my second subinterval. And so I'm looking for the area under the curve, but I'm going to use these as my approximation. Better approximation than example 1? Most definitely, right? My error here got minimized a little bit. Is it still an underestimate? Yes, it's still an underestimate. How do I write that down? Here we go. My left Riemann sum is equal to, I'm supposed to multiply the function value at the first x coordinate that we use times delta x plus the function value at the next x value that we use times delta x. This is my Riemann sum. Oh, okay. So then what is v of 0? Well, v of 0 is 1. And we know delta x is 1. Height is 1, base is 1. Plus, in this scenario, I don't know what the height is, except I have a formula, and so I can substitute it into the formula. Remember the formula we had written down was 0.5x squared plus 1. So if I substitute 1 in there, I'm going to get 1.5. And so this is 1.5 times my delta x, and my delta x is 1. So when I put these two together, I'll get 2.5. This is my approximation for the area under the curve. It's still an underestimate. However, it's a closer underestimate than the one I found over here that was way off. Well, I shouldn't say way off, but definitely not close to the actual retail price. Here, I'm a little bit closer. But if you remember, when we did in video 2, we did 4 rectangles. I'm going to show you that because we did that here. And we got an answer of 2.875. So as you can see, the more rectangles I make, the bigger the outcome and the closer that I get to the actual retail price. More rectangles means more accurate approximation. Big idea that you need to remember. All right, so now when I get to example 3, and this will be the last one for this video, what happens if I ask you to do a right Riemann sum? Same idea, we're going to have 2 subintervals, 2 equal subintervals, so my delta x from 0 to 2, I'm going to have here and here. That should be the same as what I got before, right? 2 minus 0 divided by 2 subintervals, that equals to 1. Yes. But this time, my height is going to be based off of the right endpoint, and then the next one. So this should be here, and this should be here. Well, now, these rectangles are overestimate. So the answer that I get is going to be too high, just like the answer I got here was too low. So the actual retail price, the actual area, somewhere between 2.5 and whatever I get here. So right Riemann sum is equal to, now, notice that I'm writing equal to because this is what the Riemann sum is. Now, the Riemann sum is approximating the area under the curve, but the Riemann sum equals this setup, and the setup is v of 1 times delta x. You know what? I'm going to start with the right side. V of 2 times delta x plus v of 1 times delta x. So if I'm starting from the right side, I'm going to use that x coordinate first. I plug it into the formula, and I get 3. My delta x is still 1. V of 1, we had already put it in. We got 1.5. And we're going to multiply times 1. And when I calculate all of this, 3 plus 1.5 is 4.5. So this is too much, right? This is over the actual retail price, but 2.5 was too low. So my actual value is somewhere in between. Is it exactly in between? Not necessarily. It depends on the function. Sometimes it's closer to one of the Riemann sums than it is to the other. But we're finding a way to approximate. And again, with that idea in mind that the more rectangles I create, the better the approximation I'm going to have. And people would say, well, why don't you just use a whole bunch of rectangles every time? Well, sometimes I don't have enough information to do that. And so we have to use the information we're given, and we can do the approximation based off of that.